Nobel Prize goes to Heger, McDermott, and Shirakawa in 2000 for the development of conducting organic polymers. So these are used to make organic semiconductors that have found wide use in your cell phone, your flat screen TVs, lots and lots of situations like that. There's lots of advantages for organic semiconductors over the typical inorganic materials used to make semiconductors. So that's silicon, gallium arsenide, and ITO, indium tin oxide. Cost is a big one, right? So if we can make this thing out of cheap carbon materials instead of trying to buy indium, that's going to be a huge benefit. Or if you think about ruggedness is another one. Flexibility. If these are plastics, and then now we're talking about plastics that have inherent flexibility, and that'll help us develop like wearable technologies. And finally, sustainability. Again, I'd rather not keep pulling indium and gallium and arsenic out of the ground. If I have to pull something out of the ground, carbon is maybe a little bit better for that. So the first organic semiconductor is maybe the first one that you might have come up with, right? So if I take acetylene, I get a very, very long chain of pi bonds. So this is polyacetylene. And the way I would make this conducting is to dope it. So either take out one electron, oxidize it, that's called p-doping, or add an extra electron to it. It's called n-doping. And then I've got sort of an extra charge that can sort of fly up and down this fully conjugated system. Right? Pretty straightforward. It's great as a theory, but in practice, polyacetylene really did not catch on as a useful material for a couple of reasons. One, it is too long and linear, and it stacks too well. So if it stacks too well, it's going to be too crystalline, and I'm not really going to be able to like melt it or dissolve it or anything like that. Actually, if you make polyacetylene, it looks like a metal. It's silvery and shiny, it reflects light. So it's pretty crazy. So, but that's not good for us if we're trying to, again, build a cell phone or build wearable electronics. Another thing is that because it's if you think about, when we draw molecular orbitals and I say the more pi bonds, the closer that gap between the highest filled orbital and the lowest unfilled orbital gets. Long story short, it's pretty reactive. It's pretty unstable to both oxidation and reduction. And so it's really not a very rugged material. It's going to oxidize or reduce pretty quickly. So let's iterate. Again, we want something where we've got this nice conjugated chain, but we need something that's not going to stack as well and is going to be a little bit more stable. The next wave of polymers that came out are polythiophene. And this is still the basic core of most conducting polymers today. So here we've made this quite a bit more chemically stable, less reactive, by now tying up these alkenes into essentially aromatic rings. Right? The thiophene ring is that 5-membered ring with sulfur. And thiophenes aren't quite as stable as benzene, but there is some delocalization of that sulfur lone pair into the ring. So a little bit more chemically stable. However, it's still a little bit too linear. And so how can I make this polythiophene less stackable? Right? How can I disrupt stacking so that I get something that's a little bit more flexible and a little bit less crystalline? Let's just add alkyl groups to our thiophenes. These big butyl groups, and I can tweak to see exactly which alkyl group will work the best in the situation that I want. But these alkyl groups will break up the stacking interactions, and so it's not going to stack as well, which means it's going to be considerably more soluble, which again, from a processing perspective, is really nice, right? If I'm designing some circuit, it would be awesome if I could just take some polymer, dissolve it in a solvent, just add the solvent layer to it, and then let the solvent dissolve, and just cast a film of the polymer that I want. Right? Much easier to do that than to have to melt the thing or whatever else I'm going to do. So, and again, the easier it is to make, the cheaper I'm going to be able to sell it for. One last structure I want to show you is this polyphenylene vinylene. So there's lots of organic semiconductor materials, organic conducting polymers that have this kind of structural motif. They have found a lot of use in organic LEDs. So OLEDs are widely used in flat screen TVs. That's why flat screen TVs have gotten a lot better and a lot cheaper over the years. And you can kind of see how if I want to tweak the both the sterics and the electronics of this ring, it's easy to do, right? Again, by tweaking sterics, I'm talking about, you know, adding groups to it to affect how the chains stack on each other. But I can also sort of control how tightly or loosely this ring holds its electrons just by putting different substituents on it, right? So electron donating, electron withdrawing, big and bulky, small. I've got this wide palette I can design with to make exactly the kind of materials that I want to put my flat screen electronics together, something like that. So conducting polymers is a really cool field because it gives us a lot of flexibility in our design for new compounds and new electronic materials.